One last video for us in Chapter 8. In this video, what we're going to do is talk about the effect, the common ion effect, and the role that plays in determining solubility. In the last video that we had, we determined what the water solubility of Ag2SO4 is. We determined that you could dissolve 0.014 moles of Ag2SO4 in every liter of pure water. But now let's think about what happens if you instead try to dissolve Ag2SO4 into a solution that contains a common ion. So instead of dealing with pure water, we're now going to think about what would happen if I tried to dissolve Ag2SO4 into a 0.1 molar silver nitrate solution. Will we have a solubility that's less than 0.014 molar, that's equal to 0.014 molar, or that's greater than 0.014 molar? So think about that. Go ahead and put in your answer, and on the other side of the question, we'll go over the answer together. All right, so having given you a chance to answer this question, it's helpful to recognize that in this 0.1 molar AgNO3 solution, what you have is, right, AgNO3 is a soluble compound. It breaks up completely into Ag plus and NO3 minus. And so this solution will already contain some Ag plus ion. Because the solution already has some Ag plus ion present, you will not be able to dissolve quite as much of the Ag2SO4 as you would have had you been dealing with pure water. Therefore, you would expect there to be a lower solubility in the 0.1 molar AgNO3 solution. The presence of that common ion, right, the presence of that Ag plus ion prohibits you from being able to dissolve quite as much of the Ag2SO4. Kind of comes back to some of the concepts that we talked about when dealing with Le Chatelier's principle. Now, we can actually prove this to ourselves by going ahead and calculating what the solubility of silver sulfate is in a 0.1 molar AgNO3 solution. And so to do that, we have to once again set up an ice table and find what the value of X is in the ice table. So to do this, we'll write out the dissociation for the Ag2SO4. And we'll write out the KSP expression. Now, the value of KSP is the same, right? KSP is an equilibrium constant, and as long as temperature is constant, KSP is going to be constant. So KSP is still 1.2 times 10 to the minus 5. That was given in our previous video. All right. Now we'll begin setting up the ice table. And once again, we don't care about how much Ag2SO4 solid is present because it's not part of the KSP expression. So the amount of Ag2SO4 solid does not play any role in what our answer is. In the previous example, when we were dissolving the silver sulfate into pure water, we initially had 0 for Ag plus and 0 for SO42 minus. However, this problem differs because in this problem, we're not dissolving it into pure water, we're dissolving it into a 0.1 molar AgNO3 solution. AgNO3, as shown in the previous slide, right, AgNO3 breaks up completely into Ag plus and NO3 minus. You get one Ag plus ion for every AgNO3. Therefore, the concentration of Ag plus that you have in the initial solution will be 0.1 molar, right? 0.1 molar AgNO3 means that you have 0.1 molar concentration of Ag plus initially. And we'll say that's from the 0.1 molar AgNO3. Now, the 0.1 molar AgNO3 solution does not contain any sulfate ion, so initially there's no sulfate ion present. Therefore, this reaction has to go to the right. You have to make some Ag plus, you have to make some sulfate ion. So we get 0.1 plus 2x for Ag plus, and we get x for the sulfate ion. If you just plug these values from the equilibrium line straight into the KSP expression at this point, you're going to end up with a polynomial that contains x cubed, x squared, and it's going to be a nightmare to solve. And so to make our lives easier, recognize that the value of KSP is less than 10 to the minus 3, and so we can invoke the small x approximation and approximate the equilibrium concentration of Ag plus to be 0.1 molar. That will help make our lives a lot easier. Now what we can do is plug everything into KSP, and when we do that, we'll get 1.2 times 10 to the minus 5 is equal to the concentration of Ag plus we approximated to be 0.1 squared times the concentration of sulfate, which is x. So to solve for x, you just have to divide both sides by 0.1 squared. And when you plug that into your calculator, what you'll find is that the value of x is 0.0012. And so what this means is that the solubility of Ag2SO4 in a 0.1 molar AgNO3 solution is 0.0012 moles per liter. You could dissolve 0.0012 moles of silver sulfate into a liter of 0.1 molar AgNO3. Now we can go back to the iClicker question that you saw a moment ago to confirm that this value is something that would make sense, something that we predicted. We had predicted at the outset that with the presence of this common ion, the presence of the Ag plus ion from AgNO3 would mean that you would not be able to dissolve quite as much Ag2SO4 into this solution. We predicted that the solubility should be less than 0.014, and sure enough, it is, right? So that's showing us that the presence of that common ion results in the reaction not being able to proceed quite as far to the right as it originally did when you were dealing with just pure water. With that, we've come to the end of Chapter 8. So you could take a look at these slides that are posted to Gaucho Space and see a bulleted list of topics that we covered here. This is one slide, and this is a second slide that contains a lot more information. We really did cover a lot of things in Chapter 8, and it's crucial, I think, for you to go back and rework all of these exercises on your own so that you become familiar with the strategies for solving these problems. They can seem complicated, but they can be solved in a very systematic way, and the more that you practice, the better you'll get at the system, and you'll start to find that these problems are not as bad as they seem. All right, next up is going to be Chapter 9.